Welcome to this explainer. Today, we're diving into a really fascinating intersection of high-level statistics and high-stakes investing. We're going to see exactly how complex mathematics is being used to solve a very real and historically secretive financial problem. It's basically a masterclass in how hard data science can cut right through market opacity.
Let's start with a bit of a mystery, right? The fundamental question here is, how do you measure risk when hedge funds actively hide their data? Because, let's face it, hedge funds are notoriously proprietary. They guard their trading strategies and daily positions like absolute state secrets, and they usually only release the bare minimum of information to their investors. So, if you're out there trying to build a stable portfolio, how can you accurately measure your risk with such minimal, sparse information? It's a massive blind spot for the entire financial industry.
To figure this out, we're looking at a pivotal research paper from May 2010. It's titled Random Matrix Theory and Fund of Funds Portfolio Optimization by Thomas Conlon, Heather J. Ruskin, and Martin Crane. This is literally a foundational text. It spans statistical finance, portfolio management, and risk management, and it brilliantly tackles this exact issue of hidden data by applying advanced physics and statistics directly to the financial markets.
Here is our roadmap for today. 1. The hedge fund data problem. 2. Enter random matrix theory. 3. Uncovering strategies within the data. And finally 4. Cleaning the matrix for less risk. Okay, Section 1. The hedge fund data problem.
So when you're building a fund of funds, your strategy relies on investing in a basket of different hedge funds rather than picking individual stocks or bonds. But to do this intelligently, you absolutely need a correlation matrix. You have to see how all these different funds interact with each other. I mean, if the market shifts, do they move together or do they offset each other? That correlation matrix is essentially your map of the risk.
But here is the massive catch. Because hedge fund managers are so incredibly secretive, you are usually forced to estimate this crucial correlation matrix using relatively small samples of just their monthly returns. And in statistics, a small sample size is a major problem. Relying on just a few dozen monthly data points to predict highly complex market behavior creates a tremendous amount of statistical distortion, or what analysts simply call noise.
You can kind of think of it like radio static. You're trying your hardest to listen to the pure signal, the accurate reflection of how these hedge funds actually behave and correlate. But that pure signal gets completely buried under the induced noise from those tiny data samples. It's literally like trying to listen to a beautiful symphony on the radio, but it's completely overwhelmed by heavy static. If you build a multi-million-dollar portfolio based on static, well, you are taking on catastrophic, unmeasured risk.
Which brings us to Section 2. Enter random matrix theory.
So how do we fix this? The authors proposed a definitive, highly technical solution, applying random matrix theory, or RMT. Now, this is actually a really complex mathematical framework that was originally developed in quantum physics. By applying RMT directly to the cross-correlation matrix built from those messy, noisy hedge fund returns, they can analyze its properties and rigorously identify any deviations from pure randomness. Essentially, RMT acts as an incredibly powerful mathematical pair of noise-canceling headphones.
Their methodology is basically a systematic process of distillation. First, they construct the cross-correlation matrix with the sparse data they actually have. Step 2, they apply the random matrix theory framework over it. Step 3, they quantify their findings using something called the inverse participation ratio. And finally, Step 4, they separate the noisy data from the non-noisy data.
Let's look at what happens when they do that in Section 3, uncovering strategies within data.
This is where things get really cool. When they ran this mathematical filter over the real-world numbers, something amazing popped out. The researchers' analysis revealed specific data points, in math terms they're called eigenvalues, that completely deviated from the expected random spectrum suggested by the theory. See, in a purely noisy, random system, all the eigenvalues should fit a very specific distribution. But here, a few eigenvalues were breaking the rules. They were sticking out clearly above the static.
And that leads us to the absolute breakthrough finding directly from the paper. They state, the components of the deviating eigenvectors are found to correspond to distinct groups of strategies that are applied by hedge fund managers. Think about that for a second. That is the aha moment. Those statistical deviations sticking out of the noise, they aren't random errors. They are the actual hidden strategies being used by the hedge fund managers.
The math literally forces the secretive funds to reveal their true structural behavior without them ever having to hand over a single trade log.
Just to ensure their findings were rock solid, they used the inverse participation ratio. This metric allowed the researchers to precisely quantify the exact number of components driving each of these hidden strategies. It told them not just that a strategy existed within the matrix, but exactly how many different funds were participating in that exact same underlying behavior. It effectively quantified the hidden signal.
Let's bring it all home with Section 4, Cleaning Matrix for Less Risk.
Because knowing the hidden strategies is great, but the practical application is where it really counts. By successfully identifying what was noise and what was a true strategic signal, the authors were able to transition from a noisy, totally unreliable correlation matrix to a perfectly cleaned one. They literally stripped the mathematical static out of the original matrix, leaving behind only the pure, verified relationships between the hedge funds.
So why does all this complex math actually matter to us? Well, because this technique reliably separates the noise from the signal, it drastically reduces the dangerous gap between predicted risk and realized risk. If you build a portfolio using a noisy matrix, you might predict a really low risk but realize a catastrophic loss because the math was just an illusion. But by using the cleaned matrix, what you predict is much, much closer to what actually happens. It fundamentally creates a vastly improved, way safer risk profile for a fund of hedge funds.
Which leaves us with a pretty provocative final thought. If we can borrow tools from quantum physics, like random matrix theory, to filter out the noise and expose the truth hidden inside highly secretive hedge funds, well, where else is noise blinding us to real-world risk? What other major financial dangers are just hiding in plain sight, waiting for the right mathematical filter to expose them? It's a fascinating question, and one that I really hope leaves you wanting to look at the data around you just a little bit closer.